focusing on applications and backend engineering. And today the talk is going to be around Spark streaming and Storm vis-a-vis Apex. Storm was sort of the streaming platform that pretty much everyone started with, and Spark streaming has come along the way and has done reasonably well. And we have had Apache Apex open source by DataTorrent a couple of years back, and has been picking up steam steadily. Okay, so what is Apex? I think some of you have been through the slide. It's a platform and engine runtime that enables development of scalable, fault-tolerant distributed applications. It's highly scalable. It's very performant, does in-memory computations that can reach single-digit end-to-end latency. It's fault-tolerant, as in the platform by itself provides strong durability guarantees without manual intervention. Stateful, again, you can do lights-out data processing with Apex, and you're guaranteed not to have any data loss as long as you're operating in that mode. It's developer-friendly. It's got a compositional API for operators, and more recently there have been closer to beam semantics with windowed operators and a high-level API for data scientists / data analysts. Just a quick dive into the Apex Plus RDS use cases. So typically what you see is you have a bunch of connectors on the left to talk to your input sources. For some reason, the Kafka connector is lying out of its box. Could be a formatting issue, but the Kafka guy also needs to be inside the box. And then you have the operational DAG, which is on top of Apache Apex here, which can run on multiple cloud platforms, or it's certified against all the major distros, like MapR, Hornworks, Cloudera, what have you, and it's compliant with Azure and Amazon. As long as you have Hadoop and Yarn, an Apex application is capable of running on top of it. On the right side of your screen, you have a bunch of sinks or databases, file systems, or in-memory data grids like Geo that you can write to. You have out-of-the-box support for Cassandra, Hive, etc. And DataTorrent RDS gives you real-time analytics and visualization into what is happening as a part of your pipeline. So in-stream analytics or in-stream visualization is given as a part of this suite as well. Just a quick glance at how the software stack figuratively looks. So you have your big data infrastructure, which just has to be Hadoop 2.x compliant. Comes with Yarn as the resource negotiator and HDFS as the file system. There's no prerequisite for it to be on-prem or on cloud. Both of the things are supported. On top of this, you have the Apex core engine, which takes care of all the good stuff around in-memory computations, fault tolerance, distributed containers, and orchestrating them. On top of this, you have the operator library, which is predominantly based on the compositional API, which gives you a set of operators that come packaged out of the box that you can just plug and play. For example, some of the popular ones are the Kafka input operator and output operator, both supporting exactly one semantics, and the file system input-output operators compliant with HDFS or any other file system that you will have. NFS, just give it an NFS mount and it works the same way. At the same layer, we have a high-level API and batch support introduced. If people want to deal at a batch level or sort of at a dub API level, like a builder pattern, do this, then dot this, so on and so forth. So working with transformations rather than operators, that's the high-level API flavor for you. On top of this, a bunch of application templates have been open source. So what we saw while talking to our customers, we kind of noticed that people were doing a set of processing all along, reading from Kafka, which seems to be the predominant source, and I'm sure you've heard enough about that already. So it's reading from Kafka, transforming a bunch of things, and writing to another destination. That pattern was identified, and sort of operators were matured along that path, and app templates were created. So essentially, these are plug-and-play application templates in which you can introduce custom operators if you must to leverage your business processing and not spend any time in writing the connector suite. So just focus on the business problem that you're trying to solve. On top of this, DataTorrent as a company gives enterprise suite solutions around GUI assembly, management and monitoring for ease of operations, real-time data visualization, and a few other things around the security suite. Right, just a few concepts around, that are sort of unique to Apex. So this is concept of stream locality. What that basically means is that an application developer expresses his application as a directed acyclic graph. So you have a set of processing unit, a connection which is called a stream, another processing unit which is called an operator. And by default, operators are randomly launched as a part of Yarn containers on different nodes of your Hadoop cluster. However, you have the ability to dictate where an operator should be or where two operators should not be. So stream locality is the construct that defines where operators should be placed vis-a-vis each other. So the default modes the modes that are available as a part of Apex are rack local, which means that data does not traverse network switches. Network switches often become bottlenecks, and I'm aware of a customer that we worked with. In that case, network switch was becoming a bottleneck. Then there's node local, wherein data is passed via the local loopback interface that frees up the network bandwidth again. Container local, where messages don't really need to be passed, are basically passed via memory queues between operators, and there's no need for serialization. And thread local is basically messages are passed between operators in the same thread. It's like calling a call stack in subsequent functions in a call stack in Java or any other language. Processing guarantees, yeah. So the thing is, if you take a look at some of the other streaming systems, they offer similar guarantees. However, Storm, for example, does not do exactly once. Transactional processing in a streaming mode is very, very you cannot replace an existing transactional system with a streaming system unless you achieve this exactly once mode. In Apex, we do support at least once, which is sort of the default mode. When an operator goes down on recovery, data is basically replayed back from the last checkpoint. Checkpoints happen periodically in Apex, and this mode basically guarantees that no message will be lost. You may have some duplicates because you're replaying from an existing checkpoint, and that basically means that you're going to replay a bunch of messages that you have probably seen before, but you can be rest assured that your data will not be lost. This mode can be used in conjunction with with metadata storage, rewinding of output operators, and feedback for external entities. And with idempotent operations, this kind of leads you to exactly once. Idempotency means you're seeing the same set of tuples within a given window as you had before the operator went down, or at the time that the window was being played before the operator went down. In at most once mode, this is essentially best effort delivery, right? So an upstream operator is trying to send a message to a downstream operator, and if it can send and the downstream guy receives it, great. If it cannot, well, then you don't really care about it. Honestly, I've not really seen this mode in play. This really increases the throughput of your system, end-to-end throughput of your system across all the operators. However, it's not the most practical mode to write an application in. And at least once is again, exactly once is again at least once with logic implemented for state recovery to achieve end-to-end and idempotency to achieve end-to-end exactly once. We do have a set of operators that are out in the open source. For example, the Kafka one that actually adheres to all of these constraints. And then there are window data manager interfaces to sort of write your metadata so that you can rewind from that point on as you replay the state of an operator. So that being said, exactly once semantics often come at the trade-off of latency and throughputs. However, with control tuples in Apex and window data manager implementations, the overhead of these things is not that much. All right, so let's take a quick look at fault tolerance, right? So the way fault tolerance works in Apex is that if an operator goes down, we checkpoint an operator state periodically through a checkpoint tuple that flows through every operator in the DAG. And the way it works is when an operator receives a checkpoint tuple, it sort of snapshots all of the state to a local disk. Now, snapshotting state to a local disk is kind of a good way to go about it because in cases like Storm, for example, they do checkpointing as of 2.0, which is in beta mode, but it's going to come out soon. And the way that works is that you specify a checkpoint store that is non-local. Now, that's a lot of network calls that are going to go to persist a local operator state. Instead of that, the way Apex operates is that Apex exploits local state. So initially, you write the checkpoint, which is all of the state as a part of your operator, to your local disk, and then there is an asynchronous daemon that basically copies it into HDFS, which is the default backup store. However, you have other implementations with in-memory data grids like Geode, which you can set up as the backup store. So even more performant async copies vis-a-vis HDFS. And all of this is done automatically. The phenomena of checkpointing or the action of checkpointing is done automatically by the engine. No additional work is required by the operator or application developer. All you need to do is, in case you want to disable checkpointing for a few fields, just mark them as transient and they won't be checkpointed. In case of failures, operators are restarted from their checkpointed state. So during operator launch or relaunch, all of the operator is initialized to the previously checkpointed state of the operator. The frequency of checkpointing is obviously configurable, and it's async by default with backup as HDFS. Your connectors could be running across the cluster. Your operators could be running across the cluster, and there's an application master which is tracking, which continuously receives heartbeat from these containers, and when a container goes down, it basically negotiates resources for it again and makes sure that that operator is scheduled again and or launched again with the state that it was at previous to its failure. So let's say if I have an operator which has a field called sum, and the value on that is 10. If that guy goes down, AppMaster negotiates another container, initializes it to the state 10, and starts processing, and that operator starts processing from that point on. A buffering mechanism is used to ensure replay of data and from the recovered point, so there's no loss of data. It's a buffer server. I'm sure there'll be extensive talks on buffer server at a later point. Application master state is also checkpointed, so if your app master goes down, it sort of loses context of what's going on. The app master state in itself is checkpointed, and when the app master comes up, again, so Yarn basically has a parameter for application master restarts. You can set it to a configurable value, and that restart will happen that many times. In that case, application master restarted, reinitialized to the state that it was at before the failure, and then you can start your processing from that point on, and it doesn't affect anything. So let's take a quick look at some of key concepts of Spark. So in Spark, there's a driver process, which is just a JVM that hosts a Spark context object, which is sort of the starting point of any Spark job. It's essentially the master node in Spark. In addition to this, there is a master process that is basically a running instance of this, which manages the workers and executors and basically connects to a pluggable resource manager. So Spark has multiple flavors of resource managers, works with Mesos, works with Yarn. They have a similar implementation for a local mode, just a native resource manager. Workers are essentially running Spark instances under which or in which executors live and execute a given task on different nodes of your cluster. Executor is, again, just a distributed agent for executing tasks, right? So you have the driver, you have a master, which is a process which is sort of dealing with workers and executors. Executor is running a task. And who's scheduling all of this, right? So it's the DAG scheduler. So DAG scheduler is a stage-oriented scheduler. It essentially takes the logical representation of your application and breaks it down into a physical representation using multiple stages. It usually breaks it down into multiple stages. Its responsibility is to generate an execution DAG and schedule different stages of the DAG as per the locality constraints and handles failures during shuffle, et cetera, because these will be distributed processes running across multiple nodes of the cluster. And when you're trying to ship data across, there could be failures. So the DAG scheduler is kind of responsible for handling shuffle failures as well. Now, the task scheduler is just submits tasks for execution in a Spark application. It also tracks status, like typically Hadoop would track status of a job or of a task. RDDs are another construct in Spark, which basically are an immutable distributed collection of data. Actually, it's a little more than that. It's data and the transformations on the data. So if you look at the representation of an RDD, it's not just the data that it's going to transform. It's also the transformation functions that go with it. RDDs are lineage-based. They're fault-tolerant by the virtue of lineage. Essentially, the way it works is that I'm reading from somewhere. Let's say, take the word count example, right? You're reading from a file. You're splitting it into different lines, words, counting words, right? So each of these stages is essentially a transformation. And I may have a RDD that's read and parallelize, then split into lines, next RDD, then do another transformation for words, count, and maybe write somewhere. So all of them are sort of related because one is the source of the other. And Spark's guarantees are based on this lineage. So the high-level guarantee that Spark gives is, if your source can replay the data, I can track lineage and I can recompute all of those things. So, it's a different concept. Seems to work to a certain degree, but the performance overhead of this is kind of significant because now you're recomputing and redoing everything that you've already done only because you're replaying all of the data from the start. Instead, you could just replay the transformed values and save much more. I think I'm going to go a little over time, sorry. Now let's take a look at another construct that has been exposed, which is sort of at a higher level than a RDD in Spark. This construct is tailored more for SQL kind of use cases, wherein you have data frame and data sets. So as most of you may know, data frame was sort of the older construct, and data set is the newer construct that has been introduced as of 2.0. And data frame is essentially a data set casted to a row. Data frame is weakly typed. Data sets are strongly typed. And at a representation level, it means it just says that the RDD that you have flowing through your DAG is going to be organized into named columns. Quick look at the Storm concepts. Nimbus is the master node, which is sort of the governing, which is responsible for distributing data across all worker nodes, and it basically assigns tasks to worker nodes and monitors failures. It's sort of closely related to STRAM, Streaming Application Master, in the Apex, on the Apex side. Then there are supervisory daemons which are running on each and every node, which are governing the processes, the Storm processes, and tasks that are assigned by the Nimbus, which are running on that node. Topology is, so the supervisor loosely translates to a node manager, but not entirely. Some part of the function overlaps. Topologies are the logic in which you express your directed acyclical graph in Storm. A Storm topology consists of spouts and bolts that are connected with stream groupings. A stream is basically the core abstraction in Storm. This maps one-to-one with the stream abstraction in Apex. Stream is essentially an unbounded sequence of tuples that is processed and created in a parallel distributed fashion. Spout is a special construct in Storm, which is basically an input adapter in Apex. It's supposed to read some data from an external source. Bolt is, again, just a unit of processing. And Bolt is where your code goes in as a business user. That's where you write your business logic in, or you want to deal with an external system, or write an output connector of sorts. That logic goes into Bolts. They can do anything from filtering to aggregation to joins, interacting with databases, enrichments, what have you. Zookeeper is essentially the supervisor to interact with Nimbus. It just makes sure that everyone's state is sort of checkpointed or state is maintained, and shared data is kept track of. Quick look at the Storm parallelism. So here I have a DAG that consists of one spout in blue, one bolt in green, and another bolt in yellow. The way Storm parallelism works is that you set a fixed number of executors, and then you can actually say, delegate the number of tasks within an executor. So in this case, I'm saying the parallelism of a blue spout should be 2, parallelism of green should be 2, and this guy should be 6. Total parallelism of the application or of the topology is 10, but I have also said that the number of executors for green should be 2 with 4 tasks. So that's why you see 2 big boxes with 2 tasks in each. And then number of executors of yellow is 6, blue is 2. So they are in a space of their own. Let's take a quick look at streaming, right? Now, it's kind of ironic that Spark streaming makes the cut for a streaming talk. Well, it has the name streaming in it, so sure. But it's really micro-batching, and to understand the phenomena of micro-batching, or let's go back to our Industrial Revolution days where the assembly lines were being set up. So think of an assembly line in which I am assembling parts of an iPhone or some parts of a wheel, and I'm going to assemble that part, 10 units of that part before I send it to the next guy, and then he can assemble whatever parts he has to assemble. That's batch. Let's say I reduce that 10 to 2. That's a micro batch for you. But the guy is still going to starve until I give him or hand him the control of what I'm trying to assemble. In native streaming, the construct changes. Native streaming, I assemble something, I pass it along right away. So that's a moving assembly line for you without any batching. So the platforms that do native streaming, as of now, are Storm, Samza, Flink, Apex. You can add here onto it, but essentially the same thing. So in native streaming, records are processed one at a time, and it's usually more scale out. Let's take a quick look at the architecture and features. Can I get a time check, guys? 3 more minutes? Okay, all right. So as you can see, the chart is quite big, and it goes 2 pages. So I'll take my best pass at it. All right. So in terms of the architecture and features, the programming model that's, the data processing model that's used by Spark Streaming is micro-batch, like I explained in the previous slide. Storm does support native streaming. Storm does have another high-level API kind of a flavor of it, which is Triant. And Triant focuses on micro-batching. It does not support streaming. However, with Triant, you do get some other guarantees around exactly one semantics because it's doing batches, so you can replay a batch. In Apex, it's native streaming by default, supports data in motion. In terms of the programming languages in which APIs are exposed, Spark Streaming supports very good Java, Scala APIs with client bindings for Python. Fairly intuitive for business sort of users. In Storm, you have Java with the ability to use non-JVM languages like Storm is written in Clojure, so you can use Clojure. Apex, you have Java, and there's limited support with Scala, and Python bindings are sort of coming in reasonably soon. The API that Spark Streaming uses is sort of declarative API, high-level API. So you say, transform this, read from this, dot transform this, dot do something, dub API, as is commonly known. Storm has a compositional API, native Storm. It does support a declarative API with Triant. And SQL support is available via Triant, although it's kind of not matured over the years. And not many people use it with Storm, but it's available. Apex has a compositional API, which is the DAG API. it also has a very good declarative API now. Yeah. In terms of data locality, like I explained in one of the slides earlier, it's where you want to, it's compute to data or data to compute are the two philosophies that are in use. So Spark, in Spark, you essentially schedule RDD, set of RDDs as a batch, and you could schedule them where the data is located, kind of like in the MapReduce paradigm. So you could, theoretically, you could keep on scheduling tasks where your data is. In Storm, there are some data locality constraints depending on the resource manager you're using. And with Apex, you get node local. In Apex, the philosophy is basically to take data to compute rather than compute to data, so you essentially can scale out better. In terms of latency, Spark streaming is micro-batch, so you end up with order of seconds latency. Storm is very low in a no acknowledgement mode. Triant is kind of higher because, again, it's batches. Apex is very low. It's in the millisecond range, usually. In terms of the throughput, so if you plot throughput versus the latency, theoretically, you could go to any level of throughput with Spark as long as you're ready to compromise a lot on latency. So with SLA-driven applications, that's usually not acceptable. So while theoretically throughput can be high, practically it's of limited use. With Storm, if you're running Storm in an acknowledgement mode, the throughput is kind of lower, but with no ACKs, which can lead to data losses, it's relatively higher. And I'm sure Vlad covered that in the previous talk in the Yahoo benchmark. With Apex, throughput is by default pretty high. Scalability, you have the DAX scheduler and task scheduler have to schedule tasks and RDDs in Spark, so it's kind of limited. If you're running thousands of containers, it kind of deteriorates pretty fast. Storm is, again, limited by its hacking mechanism. Storm has this notion of ACK trees, which are responsible for keeping track of data. Apex, we do horizontal scaling. Spark streaming supports very limited partitioning. Storm, again, has ability to set parallelism at worker, executor, and task level. In Apex, you have parallel pipelines and unifier support and mcross and pipelines, things like that. Connector library, Spark has chosen the model of limited certifications and more third-party integrations, where the third-party provider is maintaining that connector. It's a different model. No comments on that. But Storm, again, has chosen more recently with that model, with Hortonworks contributing a lot of connectors. Apex, DataTorrent as a company supports a lot of these Apex connectors and make sure that they are vetted as a part of the release. And Apex has integration with Samoa, Calcite, Beam, Apache Beam. In terms of state management, it's done vis-a-vis RDDs, and user has to write a lot of code with Spark. And with, with Storm, you have this notion of external stores. Redis is supported out of the box. So you could checkpoint your operator state or your spout or bolt state to a third-party store. Again, local scaling does not work out very well because you have to do all those network calls. In Apex, its checkpoint is done out of the box and works exploiting local state. Recovery, again, like I mentioned, RDD lineage. With Storm, it kind of gets interesting. You have to write a lot of user code to use Storm APIs to write to an external store, read it back. With Apex, you have the notion of buffer server, which kind of takes care of incremental recovery. Spark exactly once semantics are sort of supported at a cost of very, very limited throughput. Storm can do at least once. Exactly once needs a lot of heavy lifting. Apex, there are concrete examples out there with end-to-end exactly once. In terms of back pressure, all the systems kind of supported different flavors. User can in Spark, user can specify SLA through considerations for back pressure. In Storm, there's a different flavor wherein you can say, this is my watermark on the queue size. If you back up beyond that, then just stop putting more tuples to the next guy. In Apex, it's automatic with buffer server and spillover to disk. Elasticity, are these things dynamically scalable? Spark is, but you need a shuffle server pre-configured, and it uses an exponential increase algorithm for basically, you increase the number of partitions in exponents and decrease them in exponents with a time constraint. Storm, you can set all of those things at task and other levels through the CLI only. There's no graphical user interface to do that. Apex supports all of the above, and it's pretty elegant. Dynamic topology is an interesting concept in the sense that if I have a DAG that is doing my word count, reading, parse, count, write, can I also do an enrichment in between while that pipeline is actually running out there? Well, with Apex you can, but with none of the others. With Apex you can connect to the application, insert an operator in between, redo the streams, and run as is without any downtime. So that's a unique feature to Apex and pretty worthwhile. Security integrations, everyone supports Kerberos, but Apex also does RBAC and LDAP as a part of the enterprise suite. Multi-asset tendency, again, everyone leverages resource managers. Storm has an interesting resource-aware scheduler that goes beyond the capacity schedulers of the Hadoop world, wherein a CPU has been introduced as an additional resource constraint for the decision-making. And DevOps tools are pretty basic in Spark. Storm does have a REST API to connect with an application and a basic UI. Apex also has a REST API, and DataTorrent gives a nice UI on top of it. You can leverage the free version of that UI, I think, and also talk to DataTorrent guys. That brings me to 5 minutes of overtime. Thank you, guys. Questions, if any? Sure.
Yeah, so you talk about Spark here, and you don't talk much about structured streaming, which address some of those issues that you mentioned there. So, right. Which comes in the 2.1 version of it.
Right. So
it's
kind of recent, and yes, structured streaming is a philosophy that Spark adopted 2.0 onwards, wherein the philosophy was basically to go with, stream is infinite batches, and by the virtue of that, with things like tungsten kicking in, they have been able to achieve higher throughputs with better fault tolerance guarantees. But again, structured streaming has been more centered on the SQL side of things, wherein you combine that with the dataset API, and you're saying, I can schedule my dataset as a series of batches continuously, and I can achieve higher throughput, and then they have introduced the Parquet-based cache. But the use, in terms of the use cases that I'm seeing, it's being used more from the query-in layer and ad hoc layer than for sub-second latency streaming. The latency numbers on that are reasonably high, although in all fairness, fault tolerance has been, well, it's fault tolerant, yeah. It's not just improved.